Okay, thank you. I'm not sure how long I should review things for. Here on this board, I just captured a few of the equations that we discussed last time, so none of them should be a surprise to you. They're the definition of the partial waves as integrals of the scattering amplitude. The scattering amplitude can be recovered from the partial waves. We have the phase shifts, which is bounded in magnitude. We have this relation for the 2-to-2 elastic cross-section, given as the absolute value squared of the scattering amplitude divided by pi squared s, and then some coefficients, which yesterday I was convinced is 1/64, and today I'm not so sure about anymore. It's probably wrong. I figured that out last minute, so right now it's just some number that you can check yourself. And then the total cross-section is, of course, given by the imaginary part of the scattering amplitude, where I set t equals to 0. In other words, the forward scattering amplitude. Right? I call that forward. When t is 0, you can see that just the scattering angle x is cosine of the scattering angle, that's x equals 1, so theta is 0. It's actually a bit subtle, this forward limit, because obviously it's very hard to measure. If you have particles coming in, you can't put the detector precisely where your beam is. So people do all kinds of extrapolations and place detectors very, very close to the beam to get an idea of what the forward scattering amplitude actually is. Anyway, so that was all material.
This second formula that I know pi is missing, this one is okay, that one there are some factors.
I didn't find an inconsistency with this formula, so I think it's okay. I found an inconsistency with this one.
And when you have the elastic scattering, shouldn't both be related? And can't you use that to fix the
Yeah, go ahead. Yes, sorry. It's not so hard to fix, but I didn't have time this morning. Okay. So then, yesterday we discussed analyticity of scattering amplitude. We decided instead of going to this, staking to these physical values of s greater than 4m squared and t such that this x is between 0 and 1, between -1 and 1, sorry. We decided to continue this thing into the complex s and t plane. And then we were led to the question about how analytic scattering amplitudes actually are. And then afterwards, I discussed a few examples of Feynman diagrams and how to give singularities to the analytic scattering amplitude. And it was very clear that this function, even to low orders in perturbation theory, is not some nice analytic function everywhere. There are definitely cuts and often poles and so on. But this leads you, so this analysis of simple Feynman diagrams obviously leads you to believe that, or leads you to the question, like what would a general Feynman diagram contribute as a to the singularity structure of the scattering amplitude? So people have analyzed this question and led to the concept of a lambda diagram, which I'd like to very briefly review. And the lambda diagrams are going to tell you when a certain Feynman diagram is singular in the complex S and T plane. Because the claim is as follows, and it's very intuitive once you start working with examples, and therefore I think I'm excused from writing down a claim that's a little bit vague, but I hope after we discuss some examples, it'll be very clear what I mean. The claim is that a Feynman diagram, any Feynman diagram, is singular. Of course, I mean here as a function of S and T. Only if the following is true. I take I'll explain this word contraction in a second. Only if this Feynman diagram, or a contraction of it, can be reinterpreted as a picture, as a physical picture, a so-called lambda diagram, of what? Well, it's of classical on-shell particle propagation. This is a bit of a long sentence. A Lambda diagram. So these new pictures of, that you can associate to Feynman diagrams are called Lambda diagram. And this particle propagation doesn't necessarily have to happen in real space. I'm going to allow myself, for the particles, to move in complexified space. And the need for that should be obvious, because if we restrict ourselves to real space, we will not ever be able to move off these physical values of S and T. So we need to go into some complexified space. So what does this mean? Well, let me take an example. One example that I like is, for example, this box diagram. And internally here I have some mass m chi, and externally I have some mass m. And of course, for this, so if this 3.4 vertex exists, then it better be the case that m chi is greater than 2m, is greater than m over 2. 2m chi is greater than m. Because otherwise, my external particle would not be a stable particle, it would decay. If this vertex is non-zero, then I allow for such a decay mode. So for this, this thing to be a physical scattering amplitude, I impose this condition. Now I can do two things. Well, so now my assignment is to see how I can interpret this thing as a sort of a picture of classical on-shell particle propagation. But then there's this word contraction, which means that this contraction means that I can just take an arbitrary number of edges and remove them from the diagram. So for example, I can contract this diagram in one way by contracting this edge and that edge. And then I would get something like this, which is just the bubble diagram that we discussed before. So that's an allowed operation because I have to reinterpret this Feynman diagram or any of its contraction as classical particle propagation. So let's analyze, instead of the more complicated box, let me analyze the more simple bubble. And so I should interpret this as classical particle propagation. So I'm really looking at classical particle propagation where they have two incoming on-shell particles. They collide, two other particles come out, they move forward in time, and then after some point they collide again and two other particles, the original particles come out. So obviously, if this is going to be real space, I better associate some position x mu to this vertex, some other position x mu 2 to this vertex. All of these things can now be complex, but the usual rules just apply. For this internal thing, I better associate a momentum. This is a particle moving with a certain velocity. And for this internal thing, I also should associate a momentum and a time. And then I just say that, well, there are rules. So there's momentum conservation at the vertex, and there's also momentum conservation on the other side. And of course, there is this propagation from x2 to x1. So I see that x2 minus x1 should be equal to T1 K1 mu, and this should be equal to T2 K2 mu. And then, of course, everything should be on shell. That's another rule. K2 squared equals m chi squared, and pi squared equals m squared. So can I do this? Well, this set of constraints is not entirely trivial. So for example, I see here, from the fact that x2 mu minus x1 mu should be equal to this propagation, but also to this propagation, I find that, let me write it here, k1 is parallel to k2. But they're also of equal magnitude. So in other words, they're just the same vector. So I see that k1. So together with this constraint, I now get that k1 is equal to k2 mu. And so now I can see what kind of singularities I get as a function of the external momentum, because I can just compute together with this constraint. I see that p mu is, so p1 plus p2 squared is k1 plus k2 squared, but that's just 2 times k1 squared, which is, or 4 times k1 squared, which is 4m chi squared. So I've derived for you that this diagram has a singularity as a Feynman diagram. When S, which is p1 plus p2 squared, is equal to 4m chi squared, which is precisely what, where it should be, of course. Yes?
I don't understand the meaning of x1 and x2. If we fix the momentum, the interaction like this, how can you fix?
This is in real space, right? It's some, well, okay, I say complex space. It's a physical space. These particles are physically moving in space. This point on the board is a point in space now. And these are trajectories of particles moving with a physical momentum. And so this should be a point, and this should also be a point. You should really think of this as moving in real space. The thing is just that everything is allowed to be complex, but that's the only problem. Yes?
So saying that we're allowing a contraction of diagram can be reinterpreted as on-shell particle propagation. Just equivalent saying that we can only allow, we can say we only put some of the propagator on-shell.
Of course.
We hide it into contraction.
Of course, yes. You put the subset of the propagators on shell. Yes, that's precisely what you're doing. So this gives me the singularity of a double contraction. I hope this is clear. It's really just, right, you have to associate, one of the things that you do if you interpret this as a physical picture is associate positions to all the interaction vertices, because this is like, if this would be on a plane, it's really like billiard balls moving on a plane, and interacting with each other at certain positions on the plane. So this is just one contraction. Of course, I can do another contraction. So let me just contract a single one of the internal lines. So there's a single one that I'm not going to put on shell. And again, you can ask if this is going to give me any kind of singularity for which values of P1 and P2 can I find these vertices. So some x1, some x3, and some x2, and some set of times and set of momenta that has to flow internally, such that I have momentum conservation at each vertex, and I can interpret this as a physical process. And in fact, I said this is an exercise. So the exercise here is going to be a bit restricted because, well, the general thing is just more tedious with more sines and cosines, right? You have to see how, you have to find some angles here to see how momentum is conserved. So what I ask you to do is to take the momentum pi mu to be not arbitrary four-dimensional momenta, but let me just ask you to take them p0, ip1, 0, 0. Oh, sorry, this should be pi p0. So I'm going to ask you to restrict yourself to this momentum configuration. So you'll find some kind of singularity. That's what I promise you. And you see that what I'm asking you to do is to take the time-like component of the momenta real and the space-like component imaginary. So effectively, this sends the metric g mu nu to delta mu nu. And so you can really interpret this as particles moving in the Euclidean plane. But all these rules, of course, just work equally well for the Euclidean plane. And my promise is that if you do this correctly, you will find a singularity at S equals m to the fourth over m chi squared, and u equals 0. And t is whatever it needs to be for this to sum up to 4m squared.
But can we realize from this what kind of singularity? If this is a ball, if this is a cut?
You have to do a bit more of a sophisticated analysis. It's generically a cut, but it's not so easy to see it from just this simple picture. So this is the lambda diagram that you get from a single contraction, and as you see, it has a threshold. Well, it has a singularity where S is some value that's sort of decreasing with 1 over m chi squared, which doesn't correspond to some physical intermediate two-particle state. It's just some point on the real S-axis where this has a singularity, whose center of mass squared energy I can't really interpret as some nice two-particle state. So that's why these thresholds, and more generally, the thresholds corresponding to any lambda diagram that's not one-dimensional, they're called anomalous thresholds. So this is an example. Let me call this guy star. Star is an example of an anomalous threshold. And it happens when you have a Landau diagram that is not one-dimensional. And of course, I'm not done yet, because there's also the thing where I don't do a single contraction. So in other words, I put all the propagators on shell. Yes?
Aren't you going to impose any constraint on the range of m chi?
Well, I call this an anomalous threshold because it's a little weird, but obviously when you can see that if t, okay, then I have to give you the bit of information that I wanted to hide, but let me not hide it. T is equal to 4m squared minus m to the fourth over m chi squared for this thing. And so what this means is that this singularity, yes, it's a singularity, but it's hiding past the t-channel cut at 4m squared, at 4m chi squared, right? There's also the t-channel cut at 4m chi squared, which I can interpret as just two-particle intermediate state. This is a standard. This is exactly the t-channel version of this bubble diagram. So that's a normal threshold. And so this singularity, this anomalous threshold kicks in at a certain value, and there's a normal threshold. And you can ask, when does my anomalous threshold sort of disappear into the t-channel cut? And that happens when, so let me say, this singularity sits before the t-channel cut if m chi squared is less than m squared over 2. And physically, this is also actually understandable, because if m chi is too large, these angles here no longer become real. Everything becomes complex. So you can actually see that happening. But it's not terribly important, I think, for the big picture at the moment. So so you see that m chi squared is allowed. So if you want this thing to appear, you see that m chi squared is on some kind of, before it disappears in the two-particle cut here, you need this constraint on m chi squared. And of course, there's a finite window, because if m chi becomes too small, you get particle decay.
And when you can calculate 1.
Yes.
So then you would say that there is a singularity at some value.
Yes.
But it's not what you say.
Well, there's a singularity. So okay, this is just a T-channel cut. You can also see where it sits in the S-channel cut, and in the S-channel plane. And in the S-channel plane, I think it always sits above the 2-particle threshold. This particular one.
And try for 1 there, you get S equal 1.
Yes, but the 2-particle cut also starts at 1. The 2-particle and chi cut also starts at 1.
Of the 4. Put all masses to 1, you get S equals 1, but the cut starts at S equals 4.
Sure.
So I'm asking if we know, for example, do we know that to get to this singularity we just cross the simplest cut to go there? Which cut do we cross, or where is it?
Well, yes, there's the more complicated version, which is that you ask yourself which kind of cut this singularity can appear on. And I think more generally, there are some words that people say, which is that the cut that this thing appears on depends on whether these times are actually real or not. If they're real and positive, this thing should sit on the first sheet, in the physical sheet. But if you pick all the masses such that you need complex times, then for this to be a real picture, then the story is that generally you're on some different Riemann sheet of this complicated scattering amplitude.
Is there any graphical way of saying if it's the second sheet or third?
No, I don't think so. You would really have to think about the contour, because all of this comes. There's a whole derivation of this that I didn't give you, which is that you have to take these Feynman diagrams. You introduce Feynman parameters. You combine all the denominators. You do the loop integrals, and you're just left with an integral over the Feynman parameters, the alpha, that are typically called alpha. And these Feynman parameters are precisely these times. And you have to take my word for this. I'm not going to explain that. These times are the Feynman. But the Feynman parameters are integrated over positive alpha, alpha from 0 to 1, or if you do a bit of a rescaling, alpha from 0 to infinity. And so you basically get you can get some singularity for complex time, but it's somewhere off in the complex alpha space, and or complex alpha space. And it only hits your contour on the first sheet if the singularity actually sits on your integration contour. So that's why these times have to be positive and real, because then the singularity really hits the original integration contour. But once you start moving on the different sheets, your integration contour may get pulled in all kinds of directions, and you may see all the other singularities. But it's a bit of a tricky business. So this is actually all I really wanted to say about threshold. I can say that there's also the no contraction version. So I don't have space anymore, but there is also an anomalous threshold in this guy. Let me say, as a bonus exercise, this is a bit annoying, but you can show that this thing has a singularity. Again, if the masses are just so at some value, S, which is a function of t. And again, for specific mass configurations, the times are positive, and this thing is supposed to sit on the physical sheet. So what I'm not writing here, but what's very important is that this only happens on the physical sheet for specific mass configurations. But you see what this leads to is that if you make the value of t a little bit complex, so this is actually a real function. If you make the value of t a bit complex, this singularity also moves up in the complex S-plane. So what this thing in particular gives is we have anomalous threshold, and this guy, I say, gives, in some cases, an off, let me call it an off-axis singularity, which is a singularity which does not sit in the real S-plane as a function of t. So, okay, of course, if there was also the U-channel cut, which becomes complex, but that's in a natural way. This one is a bit more complicated. So this was just a bit of an introduction to lambda diagrams. The general topic is much more complicated. So, and I don't really have time to discuss all of that in detail because I'd like to get to some physics. So let me just say that in general, this is, seems to be a fairly complicated business, but it's algorithmic. And in principle, you can just do it. So it's complicated mostly because you get these complex times and positions and momenta. So you can make everything complex. You have the different Riemann sheets to worry about. And you often need to supplement the analysis that I gave here with some other analysis to see where exactly you are, on which Riemann sheet you are. And finally, of course, there are many diagrams. Nevertheless, in some cases, in specific configurations, there's some all-order results. For the singularity structure, say, on the physical sheet. But this is often for a fixed t real and less than 4m squared, or fixed cos theta. So sometimes there are all-order results, but sometimes it's just a more messy business. And it depends a lot on for example, the mass configurations in your theory, that like I wrote here, where these singularities occur. So I wish I could give you a more comprehensive discussion of lambda diagrams, but I'd like to continue to other topics now. So this is it for now. Are there any quick questions about lambda diagrams?
What do you mean with the last part that you can write all-order results?
To all-order in the perturbation expansion, you can show that if the mass configurations are just so, are good, then you can show that, for example, the scattering amplitude is analytic. There are no anomalous thresholds hidden. There are no anomalous thresholds on the physical sheet. All the anomalous thresholds sit on some other sheet to any order in the Feynman diagram expansion. Is that clear?
I just don't see how, because this is for each diagram.
Yes. But there's this thing that if you want the times to be real, you cannot, well, you have to conserve momentum, right? And if the masses are just so, then this angle opens up a bit too far. And if the angle opens up too far, you get basically outside your little diagram. And then you cannot get back anymore because there's no external momentum. So if you can show that the mass configurations are so that all your vertices are too wide, then you cannot complete any square or any sort of polygon in this way. Right, once particles starts moving away from each other, they have to get kicked back by something, but you just don't have that available to you. So that's roughly speaking how you get these all-order results. Oops.
Can you do this for physics or also?
Yeah, you could. I'm not sure it's an exercise I'd recommend, but yes, this works to any loop order. That's how you get these all-order results, right? Ah, thank you. Good. So now let's go to a few more results, because of course Feynman diagrams are nice, but we know that the Feynman diagram expansion does not even converge. So the question is, can you not prove analyticity or some aspects of analyticity more general? Are there not some kind of nice general theorems that that give you some clues about analyticity? And the answer is yes, there are some general results. Again, this one I'd like to be very brief, so I'll just give you some examples of axiomatic analyticity results. For example, one thing I can do, and this is what people often do, let me take my scattering amplitude and sort of partially reduce it from this standard scattering amplitude, so this is out in. And using the LSZ prescription, or the inverse of it, I extract not all 4 states to get a 4-point function, but I just extract one particle from the in state and 1 particle from the out state. So I get something like this. Time order 2-point function of phi of x3, phi of x2, p1. Right? So this thing, of course, then goes into an LSZ prescription. So what you have to do is Fourier transform this beast and put the momenta on shell, and then you look at the residue of the multiple pole. But now what I'm going to do with this guy inside the LSZ prescription is I'm going to rewrite this time-ordered correlation function as some kind of commutator. So this is a retarded correlation function. But obviously, I'm missing something. So what I'm missing is actually the Weidmann function. So this is just a simple rewriting of the time-ordered 2-point function as some retarded 2-point function and a Weidmann function. And now sometimes, again, in favorable mass cases, I can do 2 things with these two terms. So the first one is causal. Right? This is a relativistic theory. This thing vanishes for negative time differences, but then it vanishes outside the light cone. So what you use is basically that the Fourier transform, again, this is a bit sketchy, but I hope you'll get the main idea. The Fourier transform of something that looks like this is just the integral from 0 to infinity dt e to the minus, and let me now split omega into its real and imaginary parts, like so. F of t dt. But you see that since t is positive, if this thing converges for real omega, it would converge even better if I were to take the imaginary part of omega to be negative, right? Because what I do is if I move omega into the lower half plane, I just introduce an exponential damping factor. So what you can show is that this is analytic for complex omega in the lower half plane, provided, of course, it's nice and well behaved for real omega in the first place. So here you get, this is roughly speaking, very qualitatively, how you can see that this thing is analytic. I am being very fast here because there are all kinds of subtleties. For example, the fact that these momenta are on shell, you cannot independently vary the frequency without also changing the space-like components. But this is roughly speaking the picture. Now for the second bit, I can also analyze that. But to do that, to get any results about it, what I can do is, what I need to do is I need to set P4 equal to P1, because then I'm in a forward limit. And then I can say that, then I can insert a complete set of states to say that phi of x phi x3 p so we insert this complete set of states, and also that if I take the Fourier transform of whatever state I have here, and I put Q on shell, then my claim is that in some cases, this actually goes to 0. And the reason for that is basically that it's a bit subtle to see here, but you see that you have some state with positive energy, some other state with positive energy, and then, or you add some extra energy, and then it needs to go into another state. But sometimes that's just not allowed. So it depends a bit on the mass spectrum. But by stability of, for example, the external state, you can show, again, this is very qualitative, but you have to trust me that you can show that this thing goes to 0 if the mass ratios of the individual particles are in certain regimes. So again, very, very qualitative because I don't have time, but the upshot of analysis like this, I hope is probably is clear. It tells you that you need a bunch of ingredients that I've sort of implicitly used here. You need certainly causality. That's a very fundamental thing. You need something about the spectrum of the theory, something like this, and sometimes special values of t or cos theta. Right here, I set P1 equal to P4, which is the same as setting t equals 0. And only then could I say something about the analytic structure of the scattering amplitude. And these are all necessary to get, well, they're often necessary to get analyticity results. So this is, again, it's hand-wavy. You can find the details in something like Bjorken and Drell. But this is roughly speaking why you need these kind of structures. So in particular, what's very often said is that there's a very, that analyticity should somehow follow from causality. And then when people say these words, what they have in mind is arguments like the one I've given you up here. So, yep.
Is there a way of saying this vertical 2, this factor of 2 coming from this factor of 2?
So the question is if I see this square roots of 2 from my previous Lambda diagram example from this point of view, should be, yes, because I'm in a configuration where u is equal to 0, so that's the same as t is equal to 0, where I could draw this Lambda diagram. So you should see something like this. But also this is analyticity in some complex omega plane. So it may not buy you that much because this thing was sitting at real. Okay, I say could be, but the answer is maybe not, because this just gives me analyticity in the complex frequency plane. Maybe not exactly on the real axis. It's that I think this part, well, okay, it depends a bit on which particles you're scattering, but it's the fact that this particle cannot decay into those two particles with positive energy, for example. And you have energy of this plus energy of that is that. But if this particle is, say, the lightest particle in the theory, you wouldn't expect it to be able to decay.
Can you now find a relation from the possible masses and see this curve of 2 from that point?
I don't think so, because this is stability, so it would be a normal threshold, not an anomalous threshold.
Can I ask why QI greater than 0?
Yes, Q0. It's the fact that I have positive energy. Sorry. Thanks. I write no equations, and still in the half equation that I wrote, there's a typo. Sorry for So this is how people prove things, roughly speaking, from LSZ prescription. And instead of giving you detailed derivation, let me just state a few important results. So the result I like most is Bros-Epstein-Glaser result. They show that for, if I take AB to CD, general 2-to-2 scattering, and I look at the complex S-plane for any t negative or non-positive and real, then they tell me that I have cuts at most along the real S-axis. And then I think from 0 to 4m squared, there is another region where they cannot show much, which looks a bit like this. It's some region that they found. And apparently, it is called, or it was called when these people were working on it, this thing is called the potato. What they can say is that inside the potato, they don't really know. But outside of it, they have, here it's analytic. And again, the arguments that they use are more sophisticated version of these basic principles. So what do you see here is that, well, of course, if we're right here, I would have the scattering process going AB to CD. And if you have time reversal invariance, which I can assume, then over here, you would have the complex conjugate process, AB to CD star. If I would cross, like here, I would get AD bar to CB bar. Right, I move two particles around, just like I did before, and the particles become antiparticles. And so what I get here is AD bar to CB bar, complex conjugate. So this is a very nice result because it establishes at least this kind of crossing property, that in the complex S-plane, I can go from the S channel to the U channel without hitting any sort of fundamental boundaries, because any non-analyticity is hidden on either other sheets or sits on the real S-axis or sits inside the potato. So this is just part of their results. A second important result is that if you look at what happens near any of these points in the t direction, they can show that they show that you have local analyticity in S and T near any of these points. So any of the points where you outside the potato. So at least locally here, there's also some analyticity in the t direction. And of course, the size of the potato could depend on t. They don't say how the potato, or well, they do say something. So it does depend on t. Of course, the actual singularities are free to move somewhere inside the potato, but the size of the potato does depend on t. And inside the potato, you can have all kinds of singularities. But again, in some cases, for example, in forward limits with special mass spectra, you can say that. So sometimes you can show, sometimes means, for example, pion scattering, which is using just the strong interactions, of course, or pion-nucleon scattering at t equals 0. And examples like this, you can show that there's no potato. But for that, you need a bit more. Or just a simple pole. for pion nucleon scattering, there's a simple pole in the potato. So the way you easily derive that is you divide the amplitude, or you multiply it with a polynomial, and you cancel the pole, and you show that that's analytic. So you see that there's at most a simple pole. So these are two results that people have shown. As you see, it's all pretty limited. T often has to be, if you want to see what's inside the potato, you basically have to restrict yourself to very specific cases. Another result, which is actually older and comes from the Whiteman axioms, is Lehmann's ellipse. People have proven it again using the LSZ formula. And what Lehmann did is look in the complexified cos theta plane, so holding S fixed. So we're looking at this scattering amplitude, like here, as a function of x equals cos theta. And what Lehmann showed is that, well, you have analyticity from -1 to 1, but in fact you have a bigger regime of analyticity of the scattering amplitude, which is an ellipse called the Lehmann ellipse. And what I need about this ellipse is that this axis here is given by cos theta naught, which is 1 plus 2 t naught over s minus 4. And the important bit is that t naught here, so this thing is greater than 1. But this threshold value of t naught, well, there's a threshold value of theta naught, which I've translated into a threshold value of t naught, is positive, but process dependent. So you can, for example, think of this as some kind of, so you go to positive t now, and often what you hit first is either a pole or the two-particle threshold on the real t axis, and that's precisely this t naught here. So it's given by some t channel pole or cut. And of course, I should say that what Lehmann showed is that you're analytic inside the ellipse. And later, so this is what Lehmann showed, and then later also people showed that this is true for any value of S outside the potato. So there's one funny thing about this Lehmann ellipse, which is that if you take t small and positive, but you take S close to 4, then cos theta diverges, and you're always outside the Lehmann ellipse. But that seems a little weird. If I take t small and positive, I'm not expecting there to be crazy singularities. So that kind of indicates that this bound is probably not the best possible, and there's a regime of analyticity which is bigger in the t direction than just the Lehmann ellipse. And this is what we'll show in a few minutes. So let me, this is all I wanted to say about analyticity. Admittedly, it's a bit qualitative, but I hope that at least with the exercise you get some intuition for Lambda diagrams, and then if you're more interested in these axiomatic results, I would have to refer you to the literature, but these are not the most easy papers to read. So what does all of this tell us? Well, I think the first claim that, or the first thing I'd like to say is that we know relatively little about the analytic structure of scattering amplitudes in full generality. There is a potential conjecture which you can make, which is that all the singularities in the S matrix come from physical particle propagation in some complexified space, which is a bit what people assumed back in the 60s and the 70s. I'm not sure what to call it, so let me call it Landau analyticity. And this is a conjecture because again, we know very little, which is that all singularities come from lambda diagrams, lambda-like diagrams. But the particles that I'm propagating in this complexified space are not the particles that I see in the Lagrangian, as I would in Feynman diagrams, but the particles are the real physical particles. So in QCD, if I do a Feynman diagram with gluons, I may get some singularities. But what I mean here is that the only particles that are allowed to propagate in these lambda-like diagrams are the non-perturbative one-particle states. So these are things like protons and maybe glue balls and things like that. So lambda-like diagrams for physical particles. So the particles that you have in your one-particle spectrum in your Hilbert space, that of course you need all of that in order to even define an S matrix. So you definitely have that at your disposal for physical particles in, of course, still in complexified space. So whether this is true or not, I don't know. But it doesn't seem completely crazy to conjecture this, which is why I put it out there. I think we don't know of any counterexamples. And on the contrary, if you look at integrable theories in 1+1 dimensions, they basically obey this principle of lambda analyticity. So I don't think it's completely crazy to assume this and see where it leads us. And this is precisely what I'll do in the third lecture.
When you have anomalous thresholds, do they sit inside the potato only? That's the statement, or these results of the potato are for a single one?
No, they should sit inside the potato, but this is for real T negative. So what happens for positive T, these people don't tell you much about it. We'll have a small result about positive T in a minute, but that's it. Okay, any more questions? Any questions about this? No? Then let's move on to some kind of physics and discuss a few results. So, 20 minutes. Oh, I started late, right? So probably have 25 or so. So this is chapter 3. This is old results. So results where old is, according to my definition, I think at least 30, maybe 40 years. So first result is that of dispersion relation. So let me take, for example, forward pion-pion scattering at t equals 0. And I've already mentioned this. We are just completely throwing away. We're just looking at the strong part of the scattering process. So basically what people do experimentally is you have the Coulomb bit, the Coulombic part for if you have charged particles, and you just throw that away. So that's also true for the cross sections that I plotted yesterday for proton-proton scattering. Of course, because they're charged they have electric charge. The total cross section really is infinite. But what people do is you throw away the Coulombic part, and this is the part. What I've plotted should be the part due to the strong interactions only. So with that thing fixed, let me just look at pi scattering at t equals 0. In this case, this is one of these nice cases where you can show that the analyticity structure in the complex S-plane is exactly this, and nothing else, because there are no lighter states in the strong interactions than the pions. So what I'm now going to do, if this is my analytic structure, is I'm just going to take a point in the complex S-plane, and I'm going to write that T of S0 is equal to 1 over 2 pi I integral over some contour. Let me take it clockwise, because then my signs work out. T of S prime 0 divided by S minus S prime ds prime. Right, this is obviously true if I take this contour like this, because what I can do is pick up the single pole inside the contour, which is that S equals S prime, and I get exactly the answer that I wanted, which is T of S is S0. But of course, now what I'm going to do is I'm just going to take this contour and deform it. I know the analytic structure, so I'm just going to blow it up to sort of as far away as I can possibly get it, something like this. And then you see that what I get after I fold this contour along the two cuts on positive and negative S is 1 over 2 pi I. Well, you get T of S plus I epsilon minus T of S minus I epsilon, but we've already seen that this discontinuity of T across the cut is just twice the imaginary part. So let me just sub that in. So you get 1 over twice, well, 2I times the imaginary part, so that's how the 2I gets killed, and then an integral from 4m squared to infinity. So I get the imaginary part of T of S prime 0 over S minus S prime ds prime. And then, of course, I get a contribution from the left cut, but the role of the left cut is just to make the whole thing symmetric under S goes to 4 minus S by crossing symmetry. So it's just the same as saying this. And then there's a contribution maybe from infinity, so let me capture that bit into something called C infinity. But the imaginary part of T, of course, I know to be related to the total cross-section. So what I get is that this is also equal to 4 over pi root S minus 4m squared integral for sorry, this should go inside the integral. Integral for m squared to infinity, and then this is the total cross-section as a function of S prime. Root S prime minus 4m squared divided by S minus S prime. ds prime. So now what I could hope for is that this contribution at infinity, which could spoil all the fun, actually disappears.
You are setting m to 1.
S minus 4m squared. Yes, sorry. Right, this should be 4m squared minus S. And here too. So yes, sometimes I accidentally set m equals to 1. I try not to in these lectures. So suppose this scattering amplitude was very nice to us and it would fall off at infinity, so that this contribution at infinity is actually 0. If that would be the case, if I look at this, I have some interesting relation between the total cross-section, or alternatively the imaginary part of the scattering amplitude, and the actual forward scattering amplitude. So in other words, what I could do experimentally is measure the total cross-section for all energies, plug it into this equation. The total cross-section is the same as the imaginary part of the forward scattering amplitude. But what this equation then tells me is that I get the real part of the scattering, in other words, the full scattering amplitude back again. So this thing is called a dispersion relation. And it would be, in principle, an observable relation. And obviously, if this thing were to fill, then our analyticity result would be wrong. But this, as I hope I sort of showed you a little bit, this analyticity result is very, very general. And so if this dispersion relation would fill experimentally, then we would really be in a lot of trouble, and a lot of what I said is not working. And of course, it doesn't fail experimentally, and it works very, very well. And in fact, nowadays, people basically use dispersion relation to more properly measure the total cross-section at high energies. So this was under the favorable assumption that C infinity is actually 0. What if it's not 0? Well, for example, if it falls off, if the limit as s goes to infinity of t as 0, if it does not fall off, but if it behaves like, if it's polynomially bounded, so it behaves like s to the n with some n0, n greater than 0, we just pick a polynomial, Bn of s, a polynomial. Let me not call it P because that may confuse you with Legendre polynomials. Let me call it Qn of s. Then we just write a dispersion relation for, not for t, but for just t as 0, divided by Qn of s. Because that thing, oops, should, well, okay, if this is n, let me take this n minus 1. Or more generally, any polynomial of sufficiently high degree such that the thing falls off at infinity gives you, you can add it, you can divide t by it, and then of course you get something that falls off at infinity, so there's no contribution at infinity anymore. What's the price you pay? So you can see that this is of course the same as 4 over pi, whatever the integral of the total cross-section, but now divided by q, n of s prime, s prime. Some kinematical factors, s minus s prime, dot, 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 ds prime. So that's the ordinary beat, but of course the polynomial must have zeros. So we also get for m squared minus s plus contribution from zeros of q, right? Because these give me pole in this modified subtracted scattering amplitude, but no contribution from infinity. And so these zeros are, of course, a finite set of numbers, but my relation is true for all energies. So it's still a non-trivial, very non-trivial result. So these are called dispersion relations, and the things I just wrote down, where you divide by some polynomial, are called subtracted dispersion relations. Yes, that's a very good question. Yes, I think that is another thing that you can show from the LSZ prescription fairly generally, the forward scattering amplitude being polynomially bounded. So that was result number 1, classic result of dispersion relations. Before I give you result number 2, which was going to be the Fresser bound, let me give you a picture of large S scattering in the forward limit. So the premise here, the basic assumption is that high energy scattering is going to look a bit, so this is again a picture, we'll make a lot of this precise in later in a few minutes. But let me just assume that high energy scattering becomes almost classical, and it becomes black disk scattering of black disk-like scattering. So what do I mean with this? Well, you have some particle classically that comes in. You have some disk here with some radius r. And this is classical, then the important thing to look at is the impact parameter, which is the angular momentum divided by the spatial momentum. And obviously, you're going to miss this target if the impact parameter is larger than the radius of my disk. So based on this picture, we can guess something like this. We can guess that for a very large impact parameter, in other words, for very large angular momentum, I guess that my phase shifts all go to 0, so e to the 2I delta goes to 1. If I'm at very large angular momentum. And e to the 2I delta L of S. If this disk is truly black, I should have maximal absorption. So one thing I can also assume is that I'm at the center of the disk. Remember, this e to the 2I delta sits in some unit disk. And if I want maximal absorption, I should be as far away from the boundary of the disk. So in other words, at the origin. For very small angular momentum. So this is maximal absorption. Of course, what this really means for us, I mean, these particles don't disappear into the disk, but they don't come out as themselves, right? So this is maximal inelastic scattering in a sense. So what would this mean? Well, it means something. If we just plug that into the equations I wrote there on the left-hand side, you see that the total cross-section which is just the imaginary part of t in the forward limit, t as 0, but t as 0 is just given by this, with x equals 1, and if x equals 1, I use that PL1 is minus 1 to the L. So it's just the sum of all these partial waves. And these partial waves I've just given you implicitly here. So you can compute this. You can just really substitute everything into the equations there. And it's fairly easy to show that this is proportional to pi r squared times some numerical factor, which I think here is, which is 2 pi r squared. So, and also the elastic cross-section. So sorry, this should be pi r squared at very large s, as s goes to infinity. So you're basically summing 1 over some finite range of a constant over some finite range of L's. So you get something proportional to L squared, which is, right, you sum L from L equals 0 to some kind of value kr. And so that's why you get something proportional to r squared times k squared. But the k squared drops out because I have a 1 over s here in the denominator. So you can, it's a very small computation, but you get this, and what you actually get is that if you look at the elastic cross-section, it's pi r squared, and the inelastic cross-section is also pi r squared. So there is the inelastic cross-section, which is absorption by the disk. And this is this should then be diffraction by the disk. So surprisingly, perhaps it's not completely 0. It's just some finite value. So this is obviously understandable because this is precisely this absorption, pi r squared, is precisely, of course, the area of the disk. And furthermore, if you look at what this really means, is that for the FL of S, which I found here, is that when the spin is very large, L is very large, the FL of S are almost 0, so they vanish for very large spin, and they become purely imaginary for very small spin. Because if they're purely imaginary, then I can make this whole thing here equal to -1, and the phase shifts e to the 2I delta then goes to 0. So the phase shifts are either like purely imaginary or they're zero. And the only sort of regime where the phase shifts are allowed to have a bit of a real part is when the spin is of the order of kr. So what you can show is that this, of course, implies that since FL of S is purely imaginary, except for L in the vicinity of kr, you get that the real part of the FLs, but also the real part of the forward scattering amplitude itself, should be much, much smaller than the imaginary part, forward scattering amplitude. And this is actually true experimentally. It is confirmed that this, in some sense, this picture holds, at least in the sense that the real part becomes much smaller than the imaginary part. And for example, for PP scattering at very high energies, the elastic and inelastic total cross sections are are not completely. The inelastic cross section actually grows a bit more than the elastic cross section, but they're not completely up. Let me note that this radius r, which is some effective radius of interactions, can depend on S. So we can pick r to be some function of S, because this is a very qualitative picture. So why not say that this radius depends in some sense on S? Of course, then you get S dependence in all of this, so the results will be a little bit more complicated. So this is the picture. Now I want to say, I should probably stop. Okay, let me then end with, sorry?
I don't think you should start.
Yes, okay, that's fine. Let me then say that what I'm going to start anyway, but I'll stop in a few minutes. What you can ask now is, how can I pick, for example, this R of S in such a way that I maximize the total cross-section at very high energies? Can I pick some effective R of S that gives me a very large cross-section at R by picking some suitable value of R of S. And this is the contents of the Froissart bound, which tells me that I can pick an assumption for the scattering amplitude, which roughly looks like this, where there's almost maximal absorption for small spins, and then everything sort of goes to zero at very large spins. And this qualitative picture of scattering can be used to bound, roughly speaking, the total cross-section. And it tells you that the total inelastic cross-section, 2x, as a function of S cannot grow faster than some constant, which people know, times the log squared of S. So it follows, and this is for S going to infinity. And this follows from a picture that looks more or less like this, but we can make that precise fairly soon in a few minutes in the next lecture. So thank you.
So maybe while Jared and Juan in the black part, we have time for one question or two or not.
So,
Yes?
it's about the dispersion relation. For pi-pi scattering, can you also kind of write the integral for t? So,
Yeah, sure. The whole thing is crossing symmetric.
right, but you can write like integral both.
Ah, yeah. Sorry, the question was, whether I can write a dispersion relation also for t. Well, the thing is crossing symmetric. So if you take S, like obviously by swapping, and then if you can write a double dispersion relation for both S and t, that's more complicated.
For non-zero, what about non-zero? You wrote it at t equals 0?
Oh, for pi, yes. In some window of these, you can also write it down. Yes, thanks.
For the double dispersion relation, is there some obstruction?
The double dispersion relation, where you sort of write the discontinuity again as some, you write the dispersion relation for the discontinuity. There might be various obstructions. One of them is that there may be crazy thresholds. Another one that is maybe more likely to appear is that at high energy scattering, when you take S and T very large, the number of abstractions that you need grows without bound. And if that's the case, you cannot write the double dispersion relation.